All right, well, thanks everyone for joining us. We have, since we became a Keen partner, we've been doing these, trying to have at least one Keen speaker come in from the network per semester. We tried to get Rich here a lot in the fall, but there was a little tragedy at Chapel Hill. Anyway, so we're very happy to have him here today with us. Rich Goldberg is a teaching associate professor and director of undergraduate studies in the Department of Applied Physical Science at UNC Chapel Hill. He's developing an interdisciplinary engineering minor and a major at UNC. He's interested in integrated engineering with the liberal arts and an entrepreneurial mindset. Teaches a variety of classes for first-year students, seniors, and everyone in between, and enjoys designing and fabricating things in the makerspace. And with that, he's going to talk to us about empowering your students, building a foundation of skill set and mindset for successful engineers. Thanks for coming, Mike. Rich.
Great, thanks for having me. So Micah told me that you all know about Keen, so I have a couple of Keen slides here, but maybe I don't need to say anything. Just a reminder, Keen is about the 3 C's. It's not about startup companies. So building curiosity, helping your students make connections and understand about how to create value. And the entrepreneurial mindset involves both the engineering skill set, all the technical knowledge you're giving to your students, as well as the entrepreneurial minded learning, those 3 C's. So everything I talk about here is going to be revolving around that. So I'm going to start with just a quick exercise called brainstorming. And this is why we passed out the sticky notes here. So what challenges do you face when you try and implement new ideas? It could be ideas around entrepreneurial mindset or any new ideas in your classes. What challenges do you face when trying to implement something new in your classes? So just take a minute or two to do that. Write them down on sticky notes.
One idea per note?
Sure, one idea per note.
Okay.
I'll try and organize them a little bit later. Let's see what we get. All right, just another 30 seconds or so. All right, so normally I would actually have you put these on the wall. We'd organize them and talk about it a little bit more, but in the interest of time, I just want to hear a little bit from you as to what kinds of things you wrote down. So how about this table first?
I wrote time that it takes to prepare.
Yes, definitely.
I wrote lack of participant buy-in.
And
people afraid of change.
Yep. How about in the middle of the room here?
Balance with technical topics.
Mm-hmm.
Questions from students, how is this real engineering?
Yeah.
I wrote time, money, and student frustration.
Yep. All good ones. How about over here?
Some of a different one was sometimes the classroom physical space. Physical space doesn't support what I'd like to do.
Yeah.
Mine are all variations on what's already been said.
Anything in the back here?
Already the time.
Yeah. Yeah. Great. So what we just did was actually what I call a micro moment activity. And I'll talk a little bit more about this later. But basically we did, I could have had a slide up here saying, these are the kinds of things people tell me that they have a hard time doing. But instead I had you brainstorming. You were exhibiting your own 3 C's there, right? Curiosity, connections, creating value as well. So I had you do this instead of me. It took an extra minute or two of time. I could have done a little bit more, organize it and stuff like that too. But But really, without taking up much class time, you just did an activity, and I'm promoting you all, your professors, you all have the 3 C's already, but some of your students, I'm promoting the 3 C's among you right now by doing a really quick activity in the classroom. So that's one way of incorporating entrepreneurial mindset into your classes without all the pain that you were just describing to me, right? I didn't have to take a lot of time preparing it. It didn't take a lot of class time to do it. So it was a relatively painless way of incorporating EM. So by the end of this hour, my goal is to give you additional ideas on how you can incorporate EM into your classes. And again, hopefully not so painful. So what do we do at UNC? So we joined Keen in 2019, and then immediately we started what we call the faculty learning community. It's basically a faculty development program where we were trying to help our faculty understand how to promote an entrepreneurial mindset in the classroom. And it was a year-long program. We actually used our Keen money to pay them to participate in the program. And then at the end of the year, they would have a Keen card, which hopefully most of you are familiar with, so that they would publish on Engineering Unleashed, where they had their idea, and then that idea would be something that they would publish and then hopefully implement in their classes. So that was our initial thing, and here, just some of the examples of a couple of the outcomes of this from participants in this program. So on sustainability, having students develop exam questions. At that time, we were having problems with lead discovered in some of the drinking water, so someone did proposed a project around that. So that was it was a great program, successful in many ways, but our goal was to really have our faculty infuse EM all semester long, not just to do like one thing maybe at the end of the semester or just have one little project or module on it. We want an EM infused throughout the classes and so that our students are getting exposed to it all the time. And the way we were running this faculty learning program originally wasn't accomplishing this. So one neat thing about preparing for this, as I've been thinking over the last 2 weeks about coming here and giving this talk, is I realized I was able to kind of coalesce some of the programs that we've implemented and onto this continuum here. So I just came up with this earlier this week. Some of the things we did were on the micro level, things that you could do in less than one class period, like what I just demonstrated for you. Some on the mini level where it might take a class period or two, and then some where you're transforming the entire semester. So on the micro level, we had these micro moment activities that we just demonstrated. I'm going to talk about each of these in more detail over the next few minutes. On the mini level is Maker Spark, which is something that we worked with Micah on last summer with a workshop we ran. And then on the mega level, I don't know, I need to come up with a better name for this, but mind over matter is what I'm calling it for now. When I'm done, maybe you'll have better ideas of what to call it. So first, let's talk about micro moments. So what is a micro moment? Well, the definition of a micro moment in the dictionary is that it's a very short amount of time. And usually something seen as being important, but a short amount of time. The way we've been defining it at UNC is a small scale activity that you can implement in 2 to 30 minutes in the classroom. So relatively short amount of time. And what we did is looking on Engineering Unleashed and other sources, we developed a list of 25 micro moment activities. They're incorporated on this website. I'll give you the link for it later. And it gives you kind of a database of all these different activities that you can try and implement in the classroom. And they're categorized, as you can hopefully see on the, even if you're farther back, by how long it takes, so from 2 minutes to 30 minutes, and then also which of the 3 C's it's helping to promote, although many of them are more than one of those C's. So you can go through this and, I want to do a curiosity thing that takes 10 minutes or less, then you can bring it from there. We started with these lists of 25, but we hope to grow this list over time. So just as an example, here's something that I did in my class a couple weeks ago. We were talking about temperature sensors. And so I asked the students to compare the pros and cons of these different kinds of temperature sensors. And this micro moment activity is called Highlight the Best Features on our website. So thinking about thermistors, like that SpongeBob thermometer is great, but it takes about a minute to get to the right temperature. So it's not great for everything. In certain temperature ranges, it works better in than others. The infrared thermometer will work great for an application like the pizza oven, like I'm showing there, a really high temperature where you can't be in direct contact with the heat. And then the thermocouple works really well, like in an oven or measuring, in a industrial application, like in a steel mill or something like that, where you've got high temperatures, you need to constantly monitor it. So they all have different uses, and to have the students come up with this, right? Just ask the students, do some research. You could give them 15 minutes of class time where they're doing some research and they're learning a lot about thermocouples and infrared and thermistors. So having them discover it rather than me just telling them. So why are they useful? It's active learning, right? You're getting students to do stuff. They are promoting the 3 C's. And also, I think one of you over here mentioned it before about like the students coming to a class expecting just to get like equations and all technical knowledge. And it's a signal to them that like, okay, this isn't just going to be technical knowledge. I'm going to be doing other stuff in this course. And to do something like that right up front at the beginning of the semester, I think is really helpful. So it opens their mind up to like other ideas. And then another really valuable thing is that you can sprinkle these things throughout the semester, right? You could do a micro moment every class. You could do a micro moment every week, whatever you do. It's not a lot of time. It's easy for you to do. And they're getting EM without you transforming your class in any way. So we've developed a framework for this, and this is on our Keen card. We did a workshop for this at the conference a couple weeks ago. So you first figure as you're preparing this micro moment activity, think, why do you want to do it? What are you hoping that they will learn? Plan it out. In our database can be a help with seeing some ideas for micro moment activities, and then thinking about assessment. Here's some ideas for assessment. So number of responses, like I could have pulled up for the one that you did, how many responses I get. The more responses that you give, that shows more curiosity as an example. Checklist scales, you could have do peer evaluation where they evaluate each other's ideas or they evaluate their own ideas according to a rubric that you can give them. Or you can just do it without assessing it at all, but knowing that it's going to have some good impact and don't worry about the assessment. So, if you're sprinkling these things throughout the semester, I wouldn't worry about the assessment, but sometimes you might want to actually assess and see what the impact is. Just as another example for an engineering application, micro moment for teaching free body diagrams. So you could, one of the micro moments we have is called making it relevant. So in this case, you might ask a student, well, let me get ideas from all of you. Like if you were going to try and teach free body diagrams and select an article or photo related to that, or have the students select an article or photo, what would you do? Any ideas for what you do here? Think of a photo or a scene or an object or someplace where free body diagrams would come into play. Yeah.
Probably a leader carrying a
Yeah, sure. That would be a great one. Yeah, you could even bring one in, right? And walk around with it. Like, okay, that makes a free body diagram very relevant, right? What other things? Any other ideas? Yeah, go ahead.
An acrobat walking from 2 towers in New York City.
Yeah. There's the famous, for all of you mechanical engineers in the room, there's the famous Hyatt Regency walkway, right? That's a free body diagram that they forgot to do. Is the reason that failed. So, that's something that many people are teaching in their classes as well. And free body diagrams, right? If they'd only done a free body diagram, that thing wouldn't have collapsed. Any other thoughts?
We have snow and ice on the ground, right, walking.
Oh, yeah. That's a great one too. You could send the students out, have them go out for 10 minutes and find something that they think would be a great example of where free body diagram would be useful. So again, you're not taking up much class time, but think how much more, then when you come in and you're teaching them free body diagrams, now it's going to be much more relevant for them. So just doing a quick little thing like that can really have a lot of value.
Got a faculty member in my department who has the students go around campus.
Yeah.
Take selfies of them next to connections and moments.
Exactly.
So that's not a micro, that's probably a more macro thing.
Yeah.
But so they go around and they have to write reports,
Mm-hmm.
show examples of what they're doing.
Mm-hmm. Yeah. And that's a really valuable activity too. Yeah, you're going to take up a class period and then they're going to have homework and stuff. And so it's a little bit bigger thing, but you could also do that on a very small scale too. If you didn't want to have to create new assignments or transform things, you could do it as a less than a 30-minute activity. Send them out for 10 minutes, come back and talk about it. So you can do these things really easily. So next thing I want to talk about is MakerSpark. And again, we've got a MakerSpark resident expert here that I'm not going to go into a huge amount of detail on this, but hopefully this will give you a little bit of idea, and we can talk about it more later as well. So MakerSpark is something we came up with at UNC. We have a network of makerspaces at UNC. And one unique thing that we've done is that when we developed our makerspaces, we hired somebody to work, her job is to work with faculty and help them incorporate makerspace projects into their courses. So, and she works with faculty, you know, we're a liberal arts school. She's working with faculty in the STEM areas, but also working with faculty in the humanities. So we have courses come into our makerspace from every department across the religious studies, psychology, English. They're all coming in and doing makerspace projects relative to their coursework. And so that's where this idea for MakerSpark came about, is how can we kind of codify and develop a framework for what we're doing that will help people develop these kinds of projects to use using the makerspace as a way, because you're making something physical in 3D in front of you, that helps teach concepts in a way that you can't learn if you're doing stuff on paper. So that's where this idea came from. And going back, there are these things that we call threshold. This actually wasn't my invention. This is from the literature. These ideas of threshold concepts, which are things that are just a portal, a new and previously inaccessible, difficult way of thinking about something. So these concepts are really important and key, and I'll give some examples in a few minutes. They're important in the technical things that you're teaching your students. And then we also have troublesome knowledge. So these are the things that really throw students, that are very difficult to teach. They're difficult for students to learn. They may be interdisciplinary. They may challenge the student in thinking about things in a very different way. So troublesome knowledge, and we have all these kinds of things in all of our courses. The issue is that when you have a threshold concept, something that's really important in order to be able to move forward on the technical background, but it's hard to learn, you'll end up with this student crying for help, right? And I see a lot of nodding heads, like we've all seen this, right? Anyone want to give examples from their classes and where they've seen something like this? Scott, do you?
I've seen it in the method of sections, when they don't get that in statics, and then they come into mechanics of materials, and it's very difficult for them to kind of make all the connections in that class.
Yeah.
I mean, without that one concept.
Yeah. Anyone else have ideas that they can think of that's really key, difficult to learn?
So yeah, in our intro to IB courses, even last week of introducing how to calculate forces, connecting it to trigonometry or vector addition, being able to break it into X and Y components.
Mm-hmm. Yeah, I mean, so my background's in electrical engineering. Are any electrical engineers in the room? No, so this may not mean anything to you, but when you're teaching filters, and there's something called phasor notation that you need to understand. If you don't understand this phasor domain, you can't really understand how filters work. And so that's one example on the EE side.
For me, it's like values.
Oh, yeah. Yeah.
Can't do controls. But
Right. So we've got there's lots of different things that are very difficult to teach, difficult for students to learn. And if there were only a way to turn these into physical objects that could really help with the learning. So we developed this framework. And so here's the 6 steps of it. We've got first identify the troublesome knowledge, right? What are the things that the challenges that you have? And then how do you assess those objectives? So you've got objectives around troublesome knowledge. How are you going to assess them? How can you start modeling it or abstracting it into just a more general concept? And then start brainstorming ideas for makerspace activities that you could build around it, prototype it, and then test and modify. And so in the workshop we did last summer, and we're doing it again this summer. If any of you are interested, and Micah's going to be participating again this summer. So sign up if you're interested. Use some of your freebies from Keen. What we did in the workshop is we led everybody through it twice through this whole process. Once where we gave the problem, and a second time where they came up with their own troublesome knowledge from their own classes. And so the problem that we gave them was Reynolds numbers. And so Reynolds numbers are really important. It's kind of this abstract thing, right? It's this dimensionless number. And it's at some point, flow shifts from turbulent to or from laminar to turbulent as well as that Reynolds number goes up. So it's this kind of vague abstract thing. And, what if we could turn it into something real? Now, sure, you can, turn on a sink and change the flow or whatever, and you can kind of see a little bit of laminar and turbulent, but there's lots of other things that you can do that are a little bit more concrete than that. And so there's different ways that different types of activities that you can have around these maker spark ideas. So you could develop a teaching tool, right? So in this case, it would be, build a model, right? Design a model and build a model that teaches students how when you change the variables, whether the density or the flow rate or one of those other variables, how that affects flow characteristics. You could do data visualization. So here, have a physical representation of the data that you're collecting. And then also experimental models where that's more of a concrete model of it. And so here's some examples of things that people came up with from last summer. And so you can see we're not using fluid here. I think this on the left was with rice. We had like little tiny spheres, like kind of like BBs. There's all kinds of things that you can do to create flow without worrying about having water all over the place. And these are things that you can just do in a regular classroom rather than having, if you're trying to do flow with fluids, it becomes much more complicated, right? And if you got a big class of students, it definitely becomes more complicated. So, we have noticed they're making stuff out of cardboard here, cardboard and tape and just really basic low fidelity prototyping materials. They're making really simple stuff, prototyping it and coming up with an activity. This was the first shot. Obviously, more work needs to go into what they were creating there. Here, I'll run this video again so you can see this one again. They obviously have more to do, but just as a first shot, these are some interesting ideas that people came up with of a way of turning the concept of Reynolds number into something physical that students can see and mess around with. Micah, do you want to add anything from this for your experience with being there?
Well, we were in a makerspace, right? And going from ideation to realization was just kind of like an exercise of looking what was around and how you might make a physical thing out of that. I think for many participants, making something quick and dirty out of cardboard was a novel idea, right? And then, I served as a coach for the workshop, and there was a lot of, well, what are you looking for, right? Well, we need little things to rice, like BB pellets, whatever. It was kind of a fun thing of like just trying to in an ad hoc fashion, try to materialize what they were conceptualizing.
Mm-hmm. Yeah, this idea, it's interesting because we wanted to do this in a makerspace so that we had access to, the resources and the good workspace of a makerspace. But at the same time, we weren't using any of the high-tech tools in there, right? Everything was low-tech. And we had all kinds of, supplies like cardboard and plastic and stuff like that, and different kinds of fastening things. But everything was done really low-tech. And it was, as Micah said, it was really, people really discovered like, oh, wow, look what I can do with just these simple things without like 3D printing anything. And so it was really a lot of fun and to see the kinds of things that people came up with as they were working on this. Any other questions or comments or anything else you want to add, Micah?
Well, so the task of coming up with a model or a prototype that demonstrates some of these threshold concepts is something that is the ask of students to do. And so it was also an interesting thing of having people who teach a class put themselves in the shoes of a student, right? And how could I make sense of this abstract
Mhm.
idea? As these projects have continued, some of the participants have taken that, hold of that of like, this is just one of many examples that students could come up with. And some of them are like, oh, the thing I created is now a teaching tool for me to lead my students through some conceptual understanding.
Yeah. One thing that we found too is that not everything lends itself to a MakerSpark project. And in particular, some of the electronics ideas people had that the obvious thing to do with electronics is that there's all kinds of water analogies, like voltage is similar to a pump. You know, a battery is like a pump pumping water uphill, and a resistance you can get by squeezing a tube. But it just doesn't lend itself to a building something when stuff with water just gets really messy and hard to work with. And there's great videos out there, and you know, we tried to do it, we failed. That's okay. Instead, there's a case where you just show the videos in class rather than try and build something. Yeah.
Did you incorporate any calculations into, the students need to do any calculations when they were designing, when for example, the flow is going to go from the laminar to the
Mhm.
or vice versa?
Well, some of the things that people did, I'm not going to exactly answer your question because I don't remember exactly for that. But there were definitely some people who did projects related to instead of like having a graph, like they graphed. I could pull up a picture later. The making thing that they made was a physical graph, but you could manipulate and change the graph in response to different parameters. So like, there's no chalk here, but imagine making a graph out of like pipe cleaners, and then change the parameters and see how that graph changes. So still turning it into something that's physical and a little bit more concrete than just a bunch of sketches on a piece of paper, and they could manipulate them a little bit. So people did do stuff like that in working with data. Do you remember anything else, Micah?
Well, I think there was very much an inclination that what they created was something that they could measure, right? And so that the prototype could create some data that then the students could collect. I think for the most part, as a collection of engineering faculty, I think there was very much of a driven by data. And so asking them to take a step back of like, how can you take that and bring it into a physical manifestation of it and experiment with it and interact with it was more of the novelty.
And there were, I think even like people made physical tables of data where you could change out the results in them and stuff like that. Some people turned things into games too. They made little games that they could use, and so people were pretty creative in the kinds of things that they came up with for this. So this is MakerSpark, and so this is something that requires a fair amount of planning on the part of unlike Micro Moments, which is really quick and easy. This requires some planning on the part of the faculty member. It requires some class time. So definitely more involved, but also the potential for this is more significant than for the Micro Moments, right? Because you've got a piece of troublesome knowledge, students get stuck on it, and here's a way to transform their ability to learn. So definitely a lot more potential. Now I'll talk about the mind over matter. So the idea behind this is to completely transform your class into being an EM focus. And so here's some traditional courses that you'd find in a lot of engineering programs. Introduction to Engineering Design, Introduction to Material Science, Soft Materials, Introduction to Circuits. So these, we had a couple issues as we were planning our program at UNC. First of all, we are a liberal arts school. We have a major that's starting this fall. We started creating our engineering courses before we had a major. And so we needed to make sure these engineering courses were going to be accessible to a broad audience, not just engineering students. And so that was a challenge we had. We also, even once we get our engineering program going, we wanted to really have a focus on EM and also on attracting and retaining a diverse group of students in our program. And so we thought, what can we do differently with these classes to restructure them to be more accessible and interesting to students who come from a variety of different backgrounds. And a lot of these ideas really came from, I don't know if any of you are familiar with Olin College. I visited Olin a few times there in the Boston area, and it's an engineering school that just started 20 years ago, but with the idea of transforming engineering education. And so some of these ideas I got from talking to them. And so what we did is we changed the names of these classes. So instead of Introduction to Engineering Design, we called it Design and Making for Engineers, Developing Your Personal Design Potential. Instead of Introduction to Material Science and Engineering, Living in a Material World, with a nod to Madonna. Soft materials, we have a nod to SpongeBob here, engineering and soft materials, SpongeBob SquarePants, and other squishy things, which that's my favorite name of them all. And then Introduction to Circuits, it's electronics from sensors to indicators, developing electrical circuits to interact with the physical world. So suddenly now, this isn't, these classes are sounding much more inviting, interesting. You know what the applications are going to be. Even with a design and making class, like developing your personal design potential, like, wow, that sounds really cool. So these classes were restructured in a way. The content didn't change a ton, but it did change some. But the focus changed a lot. And so I'm going to go through my class, the Introduction to Circuits class, in a minute in more detail. But I'll say that in the end, you are teaching less technical content. I'll talk a little bit about what that was and what the impact of what that was. But I would venture to say that what was gained is far more significant than what was lost in doing that. So let me go through this in more detail with my electronics class. So in a typical electronics class, you're going to teach about resistors and analyzing circuits with resistors, and then you'll do op amps. I know none of you are electrical engineers, but hopefully it's not completely Greek to you. Op amps and amplifier circuits, capacitors, filters, and with each one you'll teach a little bit about it, and then maybe they'll have a lab or they'll do something where they'll learn about applications, right? So, but generally in electronics classes, the technical knowledge comes first, then the application comes afterwards. And so I think that's backwards. And so here's how I did it. So first of all, in the beginning of the semester, I talked about just some general things about sensors and characteristics of sensors and sensitivity, resolution, precision, all these general terms about sensors. Really practical stuff, right? Because engineers need to use a lot of sensors, and usually they never really get that in a class. And then the electronics topic that went along with that also was A to D conversion. Because what we're going to do is we're going to take all these signals that they're measuring in the physical world, and we're going to put them on a computer. And they need to know about sampling rate and A to D resolution, number of bits, and all these other parameters. And then they're going to learn how to do it in MATLAB as well. So all these are really practical topics, technical topics for them to learn too. Then instead of just talking about resistors, we're going to talk about resistive sensors. So what are resistive sensors? Well, you've got thermocouples, you've got strain gauges, which are resistive in nature as part of load cells. And we also use some force-sensitive resistors as well. So I teach them about the sensor. Here's how a strain gauge works. And they learn about how when you've got the gauge factor, all the different aspects, and how the sensor itself works, how the resistance changes in response to strain. They're getting those equations. They're getting all that technical stuff about strain gauges. Then they're learning about Wheatstone bridges, and they're learning about the basic resistor-based circuits and how they work. Then when you have a Wheatstone bridge, you need to have an instrumentation amplifier. So then they learn about how instrumentation amplifiers work. They're getting all that technical knowledge that I used to teach up front, but now they know why they need it, because they know they need this because they need to figure out how to take a signal from a strain gauge and turn it into a voltage. Yeah.
Are you doing this in conjunction with a lab?
Yes. Yeah. So they're building it in addition to learning the theory behind it. So they're doing all that. Yeah. So they're getting all the electronics, they're getting the sensor topics. Then we move on to optical stuff. Well, optical stuff, that means you've got LEDs, you've got photodiodes, and you've got phototransistors. And you've got a great application here in pulse ox. And in fact, I even bring in a student who does research on pulse ox on different skin types to talk about some of those issues around his research. So they're going to learn how transistors work. They're going to learn how diodes work. So all these semiconductor things, they're going to learn how they work. They're going to build the lab. They'll build all this stuff in lab, and they're going to get, again, all the electronics, but now they know they're getting it because they need to understand how these optical sensors work. Then we move on to capacitive sensors. So accelerometers, like what's inside your phone to know whether it's in landscape or portrait mode, accelerometers are capacitive in nature. They work like what's shown in that little video on the screen here. So as the acceleration changes, it's going to change the capacitance between the green plates and the blue plates. So they're learning how that works. Then they're learning how a capacitor works as well. Microphones, like you see Lady Gaga there. So microphones are capacitive in nature too. So they learn how capacitive microphones work. They're getting all this stuff, and then they're learning all the circuitry around it. How do you turn that change in capacitance into a voltage that you can then measure? And then they're doing it in lab. They're building microphone-based circuits. Then we take that as kind of a springboard to learn filters, because a signal coming out of a microphone, you might want to filter it, for example. So they're learning how filters work as well. So all this stuff they're still getting.
Does this take a bit longer than a regular teaching section? Like, let's say, editing these components for regular lab section?
Mm-hmm.
It's weird, or how do you?
Yeah, so what I'm adding before, because I used to teach electronics a more traditional way. And yeah, in the lab, they would still build circuits with microphones, and they would get those applications when they walked into the lab, but they never learned how the microphone works. And they never learned how the accelerometer works. So the stuff that I'm adding is how these sensors work. And actually that gets to my next slide here. So in the traditional format, they're getting a lot of technical knowledge the way I used to teach it. Now they're definitely getting fewer technical topics. But in the traditional format, they were getting no entrepreneurial mindset. Now they're getting those connections really strong. They're getting a lot of curiosity, not so much creating value, but they're getting a lot of connections and a lot of curiosity in the way I teach this, because it's all starting from the application. And so I didn't have to change a ton of the material that I'm teaching. Like all the technical slides that I used to have, I kept them. But what I did is I added in all these slides about how the sensors work and just theory about the sensors themselves. Yeah.
So with teaching fewer of the technical topics, do you find that then you got to cover those in a subsequent semester, or
Yeah,
by giving them the EM, do they then have the ability to go tackle that on their own?
Right, the latter is. So what did I cut? Again, this might not mean much to most of you, but Bode plots was something I used to teach, where you're doing like, it's a way of doing filter analysis. I cut most of that. They're seeing it, but they're not really doing it at the depth that they used to. I cut some more stuff about transistors, with like transistor amplifiers and things like that. The things that I cut are things that they probably will never use anyway. It doesn't matter. And if they need to use any bit of it, they'll teach themselves. They'll be fine. So you need to, so I did take out, the equivalent of several classes worth of material. Not like, so what, in a semester I've got 28 classes or something in a 28 75-minute classes, something like that. I took out the equivalent of, maybe 3 or 4 classes worth of material, something like that. But they were things that in retrospect, when I really thought about it, like, when is a student gonna ever need to do a Bode plot? 99% of them will never need to do it. And why was I even bothering? I was bothering because when I took the class, I learned how to do it. It's like, how much do we, think about what you can give up in your classes. And you don't have to go as all out as I went. I went pretty far with this. You could go less and give up less as well. But I think that the effect is transformative, because I have students from all different majors taking this class, and they're learning it even without an engineering background. Now, it's going to tighten up a little bit when our program gets started next year. And I won't be able to accommodate as many non-engineering students. I'll probably raise the bar a little bit. But by and large, I'm able to teach them a lot, even without an engineering background. And they're learning really practical stuff. Like they walk out of here knowing how to use different kinds of sensors, how to get those signals onto a computer in MATLAB. They're graphing it, they're doing like curve fitting and all this kind of stuff in MATLAB. And they're understanding on a real practical level the things that they need to know. Other questions? So in summary, I've given you different kinds of examples here. Really easy for you, easy for them, easy for class time. Definitely more work, a lot of prep work for this, and you're going to take up a couple classes. And then here, transforming the whole way that you teach, but at the same time, still reusing all the technical stuff, just cutting some of it and adding some different stuff. So here's some resources. This is from the workshop that we did last summer and doing again this summer, the MakerSpark workshop. Here's the micro-moment activities. This QR code will send you to the, actually, I'll just pull it off even. We'll send you to our web page, but let me just go ahead and pull this up. Show you. So here shows the list of micro-moment activities. And again, you can sort it like, oh, I only want to see the curiosity ones, however you want to do it. And then when you click on any of these, it will tell you more about it. So here's the activity, here's a tip, here's some examples, and some resources often pointing to Keen cards for implementation. So each one of these, there's the Painstorm one that we did, and so on. Each one of these will give you some more information about how to do it. And I encourage you, if you come up with your own ideas, like actually somebody suggested something that at the workshop a few weeks ago based on ChatGPT. You can do some really cool things with ChatGPT around this, where you have the students, plug in some search terms to ChatGPT, and I like to look at ChatGPT as a good starting point, not an ending point. I don't want students to have ChatGPT write stuff, but to get ideas from it, it's a good starting point. And so there's some interesting thoughts about how you could use that as a tool as part of a micro-moment activity. So if you have any ideas to add to this list of 25, send them my way, please. And then let me close by just acknowledging Glenn and Anna, who were part of the three of us worked together in planning the MakerSpark. Megan and I worked together on the micro-moment activities, and then the other thing with the transforming the class was something that I just came up with on my own. But definitely thank all the people that are collaborating with on this. And with that, I'll just take questions.
Thanks, Rick. More questions, Rich?
Yeah.
Sure. So I think when Pierre read your bio, I mentioned interest in connecting liberal arts and engineering education. I'm just wondering, based on your experience, what are some of the highest impact areas that you found connections?
Yeah, well, definitely with the way I talked about with my sensors and electronics class, I've been able to make a lot of connections to the liberal arts there in terms of, we'll look at comparing different kinds of sensors for different applications. So, why would you, like with the temperature sensor example I gave before, under what circumstances would it be appropriate? Don't just think about the technical knowledge, but think about if you need a temperature reading live in real time, a thermistor is not going to cut it for you. So, that's combining technical with thinking about practical considerations, thinking about environmental considerations too, both sustainability in terms of making different kinds of sensors, where are these materials coming from, how much do they cost, what are other issues around them, as well as thinking about what environment are they going to be used in, and does it make sense to put this kind of sensor in an environment where it's going to be, negative 20 degrees some of the year. So that's definitely one way that I've done it. Also, we try and think about ethical considerations of everything we do throughout our curriculum. And so we're actually in the process of trying to develop a framework around that too, because every program, I'm sure, has ethics in their capstone design, right? That's pretty standard. I want to have ethics in every single technical class. I want students to be thinking about ethical issues in every single class. So like in a material science class, thinking about, comparing these two different materials, think about performance of the two different materials and which makes sense from that perspective. But then think about this material comes from this country that there's all kinds of ethical issues with getting materials from this country and with whatever political situation is going on there, or child labor or whatever, or safety issues with people working, in the environments where that material comes from. So I want students to be thinking about this in their technical classes as they're learning the performance issues, to also the engineering performance issues. I want them to think about the other things as well. So that's something that we're trying to do throughout our curriculum. Great question. Yeah.
Just got curious about your opinion on the ethics. As a liberal arts school with religious studies, have you ever considered inviting like a religious professor or anybody in your ethics session and get their opinion?
Yeah, so one of the people that we're collaborating with on trying to develop this framework is he's a professor in I'm thinking, why am I stuck on psychology? He works with the Ethical Center and is part of developing a program in ethics. So we're collaborating with him. No one in religious studies, but yes, we are collaborating with people who are experts in this area, because we are not. I am not an expert. So yeah. So we want to get the help that we need from people who know what they're doing, because I don't. And actually, the foundation is really interested in ethics as well. I know they were supposed to have an RFP this year that didn't happen for some reason, but I know that there's something that the Current Family Foundation is very interested in. So a hot topic for the future.
All right, well, thanks again, Rich.
Thanks for having me.